simple harmonics. Okay. There's the top. Okay. So we turn off the lights. Okay. Harmonic motion refers to the motion in oscillating mass experiences when restoring force is proportional to the displacement, but in opposite directions. Is that too high up? Can you guys see all that? I'll just pull it down. Make it a little bit clearer.
What happened to your little pulled down for you?
They changed their activity because the string broke.
That's unfortunate.
Yeah. Okay, so harmonic motion refers to the motion of oscillating mass experiences when restoring force. It's proportional to the displacement. Okay. So this is probably what a ukulele looks like on the inside, right?
No, that's a guitar because
Well, I know.
ukulele only has 4 strings.
Oh.
Wait, is this the one guy? I think I've seen these videos before.
Have you? Come on, come on.
Yeah, I've definitely seen
This is actually.
No.
I could go to sleep watching this. Very soothing. What you guys notice the difference between, like, I don't know, guitar notes were like this big guy and that small dude.
The one on the left, like one to the right freaks out.
Right?
Faster. It's the low.
Oh, wow.
Is it like
Bigger one, higher frequency.
Notes are the bigger.
frequency?
The frequency is higher
Oh yeah, I see that.
I choose not to.
Why would you do
What do you do in just watch guitars from
All right. Goes on for a minute, but we got the gist. We got the gist.
No.
So what?
Are you sure?
I'm pretty sure.
Because I know, like, why are they like?
All right. So
It's more like
here are some definitions. Here are some definitions. Okay. Okay, so periodic motion, any kind of motion that repeats itself over and over and over. Period is the time to one cycle. Frequency is the number of cycles at a given time. Amplitude. Okay. So, what's the unit for period going to be? Seconds. Very good. Frequency. I give it to you. Hertz. Amplitude.
Hertz.
Meters.
Meters.
Okay. gonna pull this up for a second. So when you have a wave, here's a midline. Okay. You see how beautiful that is?
That's pretty good.
Thank you. Thank you. All right, so obviously we know our crest, we know our trough. All right, we got our midline, our wavelength. Wavelength is from crest to crest or trough to trough, right? There's our wavelength. Okay. Period, the time to complete one cycle. So, how much time did it take to complete one cycle? Okay. Then, so, yeah. And then amplitude. Amplitude is from here. Right? Is that kind of all familiar?
Yeah.
Everybody good? Got that down? Cool. Okay. So, looking at these. Okay, so I know we just got the period, but just a few more. Displacement. Hopefully you guys don't have to write displacement down. We know what displacement is. Amplitude. We know what amplitude is. Okay. A cycle. A cycle is a full to and fro motion, the same as one trip around the circle in ECM. Okay. You know, period. And frequency is the number of cycles completed per second. Okay. So there's some terminology. Okay. Everybody good? All right. Now, we're going to start with 3 different equations. Okay? Oh, no, never mind. We'll get there. Okay, so as you can see, as the position changes, the restoring force is opposite. Okay? So that's why our equation is negative. There's a negative thrown in there. Okay, just a visual. Okay? Cool. Here's our 3 equations we're going to focus on. 3 equations. Frequency is equal to 1 over the period. Okay? Angular frequency is equal to 2 pi times the frequency. And then the force of a spring. Hopefully we kind of remember that one. Force of the spring is equal to the negative spring constant times position. Okay. Everybody good on those 3? Yeah, absolutely. Looks like we got them. Ooh. You good?
Is this like negative?
You good? Negative kx, yes.
Are you actually thinking of bringing in your guitar tomorrow?
So what?
Are you actually thinking of bringing in your guitar tomorrow?
Oh, I don't have a guitar.
Do you
I
want me to bring
do,
in
I
a
do
guitar?
know how to play it though. I do. No, just that one song.
Oh.
I don't know any notes. I couldn't tell you what the top string was.
Mr. Bones, I can bring you
So
another
they do it
drink.
with citrus. I don't know. It's pretty good. It's on my car. I have 3 in my car.
What am
And I have
Mr.
3 at
Bones?
my house. And then this one.
All right, so we're going to skip the drawings. We're going to try out an example problem. Example number 1. We skipped the drawings. We're going to try example number 1. Okay. And ultra, do you guys like all the lights off?
Yeah.
Do you want one on?
No.
So here's our example. An ultrasonic transducer is used in medical diagnosis. Oscillates at 6.7 times 10 to the 6th power hertz. How long does each oscillation take, and what is the angular frequency? Okay. So, what I would recommend is always keeping our 3 equations written down. Let's always write down our 3 equations. Okay? Equation number 1. Frequency is 1 over time. Equation number 2 was angular frequency. Angular frequency is equal to 2 pi frequency. Okay? And the third one was force is equal to negative kx. Now, a little tricky because we have F and F, but both F's mean different things. We have a lowercase and a capital. Just a heads up. All right, lowercase frequency, force. Okay, so if we check this problem out, it says, how long does it take the oscillation to use? So when it asks for time, you can assume we're going to use that equation, right? So, and it gives us the frequency. So it's actually pretty straightforward, right? So it gives us the frequency. The frequency is 6.7 times 10 to the negative 7. Okay. So your answer.
10 to the
10 to the 6.
10 to the 6.
Oh wow.
The answer is to the negative 7.
It's to the
6.7.
Wait, why is it negative?
It should be positive.
Oh my gosh. I'm struggling writing this down from this problem. I'm so sorry. Okay, 6.7. I think it's because it's separated up here. That kind of threw me off. 6.7 times 10 to the 6th. I even typed negative in my calculator. Okay. So your answer for the first part should be 1.5 times 10 the negative 7. What's my unit going to be? Second. Very good. Is that what you guys are getting? Okay. And then what is the angular frequency? Okay. So we're given my frequency. Got to plug it in. Okay.
What's the unit for angular frequency?
Angular frequency, that was radians per second. Radians per second. Yep. Great question. Radians per second. So if we check this out, you're going to have 2 times 5 times 6.7 times 10 to the 6th. 2 sig figs. We're going to have 4.2 times 10. 7? Radians per second. How do we feel on that? Pretty good?
Not right now.
Yeah.
Not too bad?
Give us about 3 days and then we'll let you know.
This is the short chapter, so it won't.
This is the short chapter.
There's one thing.
Okay.
Give us
Everybody good?
Confused.
Let's try one more on this. Let's try one more. Okay, now, this involves a vibration. Okay? So, the tip of the tuning fork goes through 440 vibrations in 0.5 seconds. Find the angular frequency and the period of motion. Well, if we check out frequency, I have 440 vibrations, but it's only in a half second, right? It's only in a half second. So what's my frequency going to be? 880. Okay. Now, that's not what it's asking, but we need that in order to solve for that. Okay. Okay. Let's see, 160. 160 is going to leave me with 6,000 radians per second. Okay. And then the second says, what is the period? Okay, so we found the angular. What is the period of motion? Okay. So we know the frequency. Gotta solve for the period. Which is, so the period, I got 1 times 10 negative 30. We feel pretty good? So you guys got?
Yeah.
Okay, so my frequency was 880, and to find period, so my period is time, right? So I plugged 880 into this equation. So that was my frequency. So you can just flip-flop those, right? So 1 divided by 880 is equal to time. Does that kind of help out? That's how you find the periods. Okay? Now, last thing I want to talk about is harmonic energy. Okay? And what's crazy is we already know most of this, right? For example, what's my kinetic energy? Okay? That's already half of it. That's pretty crazy for the total. Now, does anybody remember the kinetic energy of a spring?
1/2 kx squared.
You already know it all. You already know it all. Okay?
I don't know, those are easy.
Okay. So, got a little video we're going to watch, then I'll show you the equations here, and we get to go.
In June 2001, officials in London unveiled a striking new feat of engineering, the molecular energy.
You seen this?
No, I've seen about that bridge.
Cool.
Have, and what's its maximum velocity? To better understand what's happening to the ball, let's start with its energy. As the ball compresses and stretches, the spring, both kinetic energy and potential energy come into play. Kinetic energy is the energy of motion, and as the ball moves, there are 2 points, the turning points, where it's not moving. One point is where the spring is compressed all the way, and the other is where it's stretched all the way. And the distance between either of these 2 points and the equilibrium point is called the amplitude. At those 2 turning points, the ball won't have any kinetic energy since it isn't moving. Instead, all of the ball's energy will be potential energy from the spring. Half of the spring constant times the amplitude squared. Now, as the ball moves towards the middle, its kinetic energy starts to increase because it's moving faster and faster. And at the same time, its potential energy decreases, keeping its total energy the same. And exactly in the middle of the ball's motion, at the equilibrium point, its potential energy goes down to 0. The ball is back where it started, so the spring is no longer pulling on it. Its kinetic energy, on the other hand, has reached its maximum, which means that at that point, the total energy of the ball will be equal to half of its mass times its maximum velocity squared. Now we have 2 equations for the total energy in this oscillating spring, which we can combine into one equation. And if we use algebra to move around its variables, we can start to answer the second question we had about the ball. We wanted to know the ball's maximum velocity, and this equation tells us that it's equal to the amplitude times the square root of the spring constant divided by its mass. So we've answered our 2 questions about the ball and the spring. We know about its energy, and we have an equation for its maximum velocity. But there's a lot more going on with this ball than just its energy and velocity.
He goes on and on. That's a good pause face right there.
She said equilibrium.
Britain, man.
They
They say aluminium.
Aluminium.
There's no I there, is there?
No.
Talk about
Okay, so here is our energy equation.
I say aluminium.
No, you're good.
I was reenacting a scene from APP1. One of the worst movies I've ever seen in my life.
Oh, you guys talking about the turkey?
No, you've seen it. You don't, but it's a great game. You ever played the game, everyone?
You don't get to talk.
So
it's not like the movie.
I'm going to tell you the game and see if it's like the movie.
Okay.
So the game. There's always a mission leader. Okay.
Yes.
And
No.
on the they assign a few people to go on a mission.
Yes.
Now, there's a red team and a blue team. The red team tries to fail a mission, but you don't want to get caught. Okay, so you try to lie your way out of the mission. All right, and pretend it was somebody else.
Yes.
It's not this.
No.
No.
This
It's about an
so
immigrant
we're
family.
watching this movie because we just read The Jungle, and this movie is like not a best representation of the jungle at all.
Yeah.
But like
It's
it
a
has
stretch.
a little bit to do with it, but like not much at all.
Fair enough.
Well, it's not the jungle. He was just like, oh, this is similar because it has immigrants in it.
Yeah.
Alright.
That was basically it.
Yeah, that doesn't matter.
So-
At all.
I
It
know.
really does.
If we check this out, when we hit our limits, when we hit our 2 limits, when either the spring is completely compressed or when the spring is completely expanded, that's when all our energy is potential. All right. So energy total is 1/2 kx squared. Okay. When it's kinetic, we can say our total energy is 1/2 mv squared. But the total energy, mechanical energy, is always going to be conserved. Does that part make sense? Yeah?
Total mechanical energy is conserved.
It's always going to be conserved. So initial is always going to be the same as final. Okay? And that's probably all we're going to get through today. Okay? We got about 3 minutes, 2.5 minutes left. All right? My front light's coming on, 3, 2, 1. Back light, 3, 2, 1. All right. Tomorrow, we're going to analyze a ukulele sound.
Yeah.
Okay. I'll get you guys back your test. We'll go over the test. And we'll see where that takes us. All right. If we have time, I want to try my telephone. My telephone. It's a super easy, short activity, but it's pretty fun.
Oh.
Say what? Yeah. So I'm curious because I've heard from like everybody I've had that Miss Kruth is super awesome.
Miss
Like,
Kruth-
what's she do?
Oh, she's just a really good teacher. Like she just like
She
goes in depth.
like she
Very
goes
well.
in depth and she like just the class is fun. It's not boring.
Yeah.
Like even when you do it's kind of like in here. Like even when you do notes, it's not boring.
Fair enough.
Like
I get that.
it's like and she does a lot.
I had
I know
her-
it's just in chemistry generally you do a lot of labs.
Yeah.
Yeah.
But
Group work was nice.
you do a lot of labs, a lot of group work, projects. It's just like
Good atmosphere.
yeah, it's just in general she's just a good teacher.
Yeah.
Like you just learn the stuff without learning.
Because I've this is my second year here. I've been trying to observe all the teachers and I haven't observed her yet.
Yeah, she is just really. I mean like the difference between her and
That was really loud.
Houston, like people that have
Ooh,
Houston,
national
like
high
I
five
could
day,
take
though.
Houston and I could get like I probably like do good. Like I probably still keep a 4 point, but like in proof I had 140.
Wow. Yeah.
So I mean it's just like the
No.
I don't know necessarily like she doesn't teach like hard, but like you learn better.
Yeah.
Because there's no exam anyway, so it doesn't matter.
Right. Right.
Like
I liked her class. I had her for bio.
her class is
My sophomore year.
Yeah, she teaches bio as well.
Interesting.
Yeah.
A lot of most of the
But,
science
like-
teachers teach like you, they teach multiple.
The
Yeah,
other,
yeah,
the other
levels
thing
of-
about her, like, if you go up and ask her a question, she won't just be like, "Oh, it's right here in the notes,"
Oh, no,
She'll, like, actually explain it to
Yeah.
so that you understand.
She does notes of, like, she also like, one of the things is she uses like whiteboards.
And
So like
for-
when she asks questions, kind of like we do for like the,
I love being the hallway, man.
oh no. We're all about to get it, aren't we?
Oh, that was.
Oh.
Is it a video?
Oh, okay.
This app I have for bands. You can like choose different pitches and different. I was like, oh my god. If you take a sine wave and you do these exact same pitches, you can limit
Oh wow.
Have a good day.
That sounds like it's
all the way down.
It does sound like Amber.
I know everybody started getting their phone
Please
out.
report to the library.
I didn't want to start
Yeah.
Megan Gibbons, please
Ukulele.
report to the
I didn't
library.
mean to start that.
No, you're good. It really sounded like it.
It was relatable and fascinating.
Uh-huh. So you use that for band? Is that what you
Yeah,
said?
it's a tuning app.
Oh, okay. That's pretty cool.
Maybe I should bring in my trombone or my tuba.
We could just have a little concert in here, you know? That'd be pretty impressive. Are those your earphones or charger or whatever that is?
Those are not mine.
Nah, just leave it down there.
Okay.
Yep.